Before we start calculating what kinds of energy there are and talking about energy, let's just talk in general about energy. And of course, energy is defined as the ability to do work. And the reason why that's funny is that, of course, we defined work as a transfer of energy. So, as a student, you really should get the idea that nobody really knows what's going on here, right? This is a circular definition. Energy is a somewhat intangible thing. Only I'm going to make it very quickly here, very tangible, right? Energy is sort of what makes things go, right? So the energy in a gasoline makes your car go. The energy in natural gas makes my furnace go. The energy that you store when you charge the battery on your phone makes your phone go. And of course, it is used up, right? And when I say used up, it doesn't mean it's destroyed. It's just like in the case of your phone, it actually turns into heat and electromagnetic energy that ultimately turns into heat and stuff like that. Um, so that's the idea, right, behind energy. And then this is the reason why we're studying it is that it's neither created nor destroyed. It just moves around. So, for example, if a car rolls down a hill, okay, at the beginning it's got potential energy, and at the bottom of the hill, okay, you know it's moving because it's got those lines after it, right? Or before, yeah, right. Okay, so here it's got kinetic energy. The exact amount of potential actually turns into the kinetic energy. So it's a pretty useful concept, right? And then this is the challenge, right? We'll talk about this. There's a challenge, and what I want you to do is come up with some kind of energy you're aware of that you think is not nuclear. And in class, one of the things we'll do is we'll talk about how it probably is nuclear. Okay, most of the energy that you encounter in your life is nuclear. Okay, there are four types of energy that we're going to talk about here. So the first one is electromagnetic energy, the energy of photons, right? The idea is light is made up of little particles, right? We draw them like this, but we don't really know what they are. And they've got a certain amount of energy, right? That's actually some constant times the frequency of the light that they represent, right? And this is Einstein's great idea, right? And ultimately, energy can turn into matter, right? E equals mc squared, right? So energy and matter are the things that are conserved. And this is an interesting thing because if a small amount of matter goes missing in a nuclear reaction, multiply that by the speed of light squared, well, that's 3 times 10 to the 8th meters per second, right? That squared is 9 times 10 to the 16th. That's an enormous number. So some small amount of matter missing in a reaction means that you've released a tremendous amount of energy. And prior to the end of World War II, they discovered single nuclear reactions that were giving up 200 million electron volts of energy. That's just a very small unit of energy, right? Typically, explosives give off tens of electron volts of energy, right? These reactions were giving off 200 million electron volts of energy, which was just pure conversion of matter into energy. This is, of course, we're talking about nuclear bombs. But all of the energy, all of the matter that you see around you is actually just condensed energy, energy that has stabilized itself as mass in various resonant states like electrons and protons and stuff like that, right? So matter really is just condensed energy. All energy started off as some kind of electromagnetic or something like that energy in the Big Bang, and it's condensed out. The next type of energy is potential energy. This is stored energy, right? So if we have a mass, we could have it sitting on the ground, but we could also lift it up, right? It has more potential energy when it's in this position than it does when it's in this position, right? Or we could have a spring, and then we could stretch the spring, right, some distance, and this has energy because it's stored, it's in that position, right? We could have 2 hydrogen atoms bonded to each other plus an oxygen, and that could turn into 2 water molecules. Well, this is a tremendous amount of potential energy. This is what propels the space shuttle into, or did propel it into space, right? So anything that depends on position is potential energy, right? And then kinetic energy is just the energy of motion, right? what do we have some examples of this, right? A baseball, right? This is why you wear a helmet, right? A baseball hurts, right? Anything that's moving has something called kinetic energy. Uh, a hammer is sort of an interesting thing, right? You want to drive a nail in, so you swing a hammer, right? The hammer is moving, and when it strikes the nail, it pushes the nail in some very small distance, right? So the kinetic energy turns into work pushing that nail in, right? So Superman would just like push the nails in by hand, but there it is, right? And then thermal energy finally is just random kinetic and potential energy of molecules and atoms. I like my examples, hot stuff, right? Okay, but this is the idea, is that this is a solid, right? Imagine that this thing is really just a bunch of steel ball bearings connected by springs, right? We can draw all these little springs like that, right? And they're just vibrating back and forth on the springs. And when they're moving, of course, that represents kinetic energy, like this guy's apparently moving in or out or something like that, right? And when they are stopped, when this guy's moved as far this way and is about to start going back this way, right? When it's stopped, it's got the energy stored in those springs. And of course, those are probably like electrostatic forces or something like that, repulsion of positives and positives or something like that, right? But the reason that we tend to categorize this separately is that it's so random. And there are laws of physics that say that you can't take, if you have 10 joules of thermal energy, you can't actually turn that. You cannot turn that into 10 joules of, say, kinetic energy of a baseball or something like that. Some has to be wasted. This is is that the second law? It's the second law of thermodynamics. Anyway, I hope that helps. That's just an introduction to energy.